In this video, let's look at how we may identify if we solve a problem using simplex algorithm, and then it turns out that we do not have just one single optimal solution, but we have a lot of solutions, optimal solutions. In other words, we have alternative optimal solutions. So if you recall, there are four possibilities when we solve an LP model. So it may be that the solution is unique, or we have an alternative solution, or the LP model is unbounded, or maybe the LP model is infeasible. So let's look at the second possibility where we have alternative optimal solutions. We are going to use this modified example of the Dakota Furniture Company that we've seen on the week 4. So the difference between this example and the previous one is that the price of the table is modified to become $35. So everything is the same. The only thing that changes is the price of the table is now $35. I think it was like $30 before. Okay, so I will give you a pause on the video to read this example again, get all the information and understand the problem. So that is the formulation for the modified example of the Dakota problem. So the price of the table has been modified to become 35. And then we convert this into a standard form. So because all constraints are in the form of less than or equal to, we are adding slack variables, S1 for the first constraint, S2, S3, S4 for the following constraints. And then do not forget to say that all Si must be greater than or equals to 0. So this is our standard form. So from the standard form, we put the standard form in this table, and we see that we already have a BFS because you have a canonical form, and then you also have all basic variables. They are all positive, so it is a BFS. Step 3, you ask the question, is this BFS optimal or not? It is not optimal because you still see coefficients with negative values in row 0. So you have x1, x2, x3, they're all having negative coefficients. So this BFS is not optimal. Then you go to step 4 to pick x1 as the entering variable because it has the most negative coefficients. In the case of maximization, you pick the most negative coefficient to become entering variable. And then you perform ratio test, pick the smallest ratio test as usual as the winner. So now you know S3 is the leaving variable. In step 5, you perform arrow or elementary row operation with the intersection between the entering variable and the leaving variable as the pivot, which means that you try to make the new table such that this pivot here becomes 1. And all the other values in this column, they must be 0. So that's what you're trying to do by doing arrow from the table above to the table below. Now, again, once you've finished all the arrow or elementary row operations, you ask the question again in step 3. Is this BFS optimal? Again, the answer is no, because you still have x3 is the most negative coefficient in row 0. So you perform ratio test again, and then you pick the smallest one, and then you will perform arrow with that value, that position here as the pivot. Okay, so this is what we have from the previous slide. So x3 is the entering variable, s2 is the leaving variable, and the pivot is here. So our new table must look like this. In the column x3, the pivot should become, not should, but must become 1, and all other values in this column becomes 0. So here, once you have the new BFS, after you finish all the elementary row operations, you ask the question again, is this BFS optimal? Yes, it is, because for the maximization case, you do not see any negative coefficients in row 0, so indeed we have reached an optimal BFS. However, you see that you have a non-basic variable, so x2 is a non-basic variable, but the coefficient in row 0 is 0. Usually what we've seen so far is that row 0 is only 0 for those who are basic variables. So those in the canonical form, they have row 0 equals 0. But now we see that x2 is a non-basic variable, but it has a row 0 equals 0. So what happens if we try to enter x2 into the basic variable? So that's what we'll see next. So if we try to enter x2, which is a non-basic variable, but the row 0 has the value 0, so we're trying to enter x2, we perform the ratio test, and then it is not shown here, but this one has the smallest ratio test. So we are going to perform elementary row operation with this position as the pivot. So this is our new table. So the position of the pivot becomes 1, and all the other values in this column become 0. Now you see here that x2 becomes a basic variable. So x2 becomes basic variable, x1 leaves the basic variable. Now you see x1 becomes non-basic. But then the same thing happens again. x1 is a non-basic variable, but the coefficient in row 0 is 0. So what happens if we try to enter x1 into the basic variable? Well, you will return to the table above. You enter x1 into basic variable, you will kick x2 out from the basic variable. And then if you do the same thing again, you will return to this table. So you will have these two tables going from into one another. So you just exchanging x1 and x2 to the basic variable. So the table above is optimal. The table below is also optimal. So both tables are optimal. But here we have alternative optimal solutions because the clue or the sign is that you have a non-basic variable on your optimal table, but that non-basic variable has the coefficient 0 in row 0. Okay, so let me repeat. You have an optimal table, but you see a non-basic variable has the coefficient 0 in row 0. That's the sign that you have alternative optimal solution. And how to obtain the other table that also contain the optimal solution? You enter that non-basic variable with the coefficient 0 in row 0, and you will get another table which is also optimal. So that's how you identify the existence of alternative optimal solution and how you get another table which is also optimal. Now here's the more complete interpretation. The first table is optimal, means that we have first extreme point from the first table. The second table is also optimal, means that we have the second extreme point. Remember, in the case of the alternative optimal solution, it means that not only the extreme points, all points between those two extreme points are also optimal. So let's look at the first extreme point. So the first extreme point is x1 equals 2, x2 equals 0 because it is a non-basic variable, x3 equals 8. For the second extreme point, x1 equals 0 because it is a non-basic variable, x2 equals 1.6, x3 equals 11.2. Why we don't care about S1, S2, S3, and S4? Because what we really care in the problem is the decision variable, right? In the Dakota problem, x1 is the number of desks that you produce, x2 is the number of tables, x3 is the number of chairs. So that's why we don't write down the slacks. But if you want to, you may, but in the real problem, you only care about how many tables, desks, and chairs you produce. So that's why we write down only x1, x2, and x3. Okay, so go back to what I said before. In the alternative optimal solutions, not only these two extreme points are optimal, all points between them are also optimal. How can we say that in a mathematical language? Well, you can do this. You do something called linear combination between these 2 points. So 208 and then 0, 1.6, 11.2. You multiply them with C for the first one and then 1 minus C for the second one. But there is a strong requirement for the C. C must be between 0 and 1, including 0 and including 1, but cannot be less than 0, cannot be exceeding 1. So this is how you say that all points between the first and the second extreme points, including both extreme points, are all optimal. Okay, so now let me ask you a question to check your understanding. In a maximization case, and then given the BFS on the table, there's a statement saying that the BFS is not optimal because x2 is a non-basic variable, but its row 0 is 0. So the statement says in this kind of condition, this BFS is not optimal. Is this true or false? I will give you the answer after the pause on the video to give you the time to think about the answer. The answer is false. Here we have a table or BFS that is optimal because in a maximization case, if you see that your row 0 does not contain any negative coefficients, it means that this BFS is already optimal. However, when you see that the non-basic variable like x2 has a 0 in the row 0, it simply means that our optimal solution is not unique. We have a lot more alternative optimal solutions. It means that actually we have infinite number of alternative optimal solutions. So up to this point, you should be able to solve a problem using simplex algorithm and then determine whether you have a unique optimal solution or you have alternative optimal solution. And then if you have alternative optimal solutions, you should be able to find out to obtain a lot more of that alternative optimal decisions. That's what I'm going to ask you in the next slide. So given this all results, the first extreme points from the first optimal table, second extreme point from the second optimal table, and then the linear combination of how we may describe all the optimal solution, can you write down 7 optimal solutions of this problem? Actually, I can ask you like 7, 12, 30, 100, 1,000 or anything, but let's just try to write down 7 optimal solutions of this problem. You should be able to do this. Okay, so this is the end of the video. See you in the next one. Thank you.